Hello and welcome to today's last session, the last session of the day 2 of MobiliT.AI in 2021. So today, to conclude this series of conferences, we have gathered a panel, a discussion panel of experts in the domain. And so they will talk about what guarantees for AI. And so let me introduce you the moderator of today's panel, who is François Laviolette. François is a full professor at the Faculty of Science and Engineering at Université Laval. He's also the director of the Research Center of Big Data at Université Laval, a member of Institut Intelligence et Données, as well as a principal investigator of the DEAL project in Quebec. So welcome, François, and the floor is yours.
Thank you very much, Fabien. So we are continuing the panel of yesterday that was about how we can certify AI. For now, yesterday, the panel was basically constituted of people from the industrial point of view and the certification agency point of view and stuff like that. And today we have the panel, but from the point of view of the academic. So we have 3 people that are related to the DEAL project, that are really involved in the DEAL project. Both of them gave a very interesting talk this morning. If you missed them, I really suggest that you should look at the YouTube recording about that. And so let me briefly introduce them. So the first panelist is Edouard Pauwels. He's a lecturer at Toulouse Paul Sabatier University. He conducts his work at Toulouse Computer Science Research Institute. It basically in argumentation, decision reasoning, uncertainty, and learning ideas. His research focused on digital optimization, its application in artificial intelligence, and how can we gather guarantee out of that. So, bienvenue, Edouard. The second panelist is Jean-Michel Loubles. He's a professor of applied mathematics at the Institute of Mathematics of Toulouse. He is the holder of the Fair and Robust Learning Chair of NET. After a thesis in Toulouse and Leiden, he has been a researcher at the CNRS, at the University of Orsay, and then at the University of Montpellier. Since 2007, he has been a professor in Toulouse, leading namely the statistics and probability team. So really a strong theoretician here. His current research focus on one end on the application of optimal transport theory. We will see it. It's very interesting what we can do with that in the point of view of certification of AI. And more especially, he is an expert about fairness and robustness in AI. The last panelist is Liam Paul. He's a professor at Université de Montréal. He's related to the MILA, the MILA lab. Yeah, also, his research focus on robotic issue, not only, but the idea of how can we build a representation of the world that will be robust. Previously, Liam was a researcher at the MIT, where he led the self-driving car project. He also has a postdoc position at MIT in the Marine Robotic Lab, where he worked on the SLAM for underwater robots. He received his PhD from University of New Brunswick in 2013, where he worked on robust and adaptive planning for underwater vehicles. And he is also the co-founder of and the director of the Ducky Town Foundation, which is dedicated to making engaging robotic learning experience accessible to all. from the DEAL project. He's the leader of the robustness axis in the Quebec part of the DEAL project. So I'm pleased to have you, three of you. I will start with a very simple question. What is robustness, and what robustness has some interest from the certification point of view in AI? Who wants to start? Liam, maybe?
I can start. Yeah, sure. Since I'm the head of the robustness axis. Robustness has a very precise definition, actually, in control theory. The notion of robustness is the idea that for a controller is that it will be able to account for variability in the system that it's trying to control that was not modeled at the time that the controller was actually built. And this is a design criterion that is orthogonal to performance. And while all of the, I think, metaphor from the control theory doesn't necessarily apply, I do like this notion of, that robustness in some way captures our ability to handle uncertainty or unforeseen events or unmodeled effects. And I also like the notion that it should be treated as something that is orthogonal to performance. We should be able to evaluate our models along these different axes in some way independently. And hopefully we can find solutions that are good along both axes, but it's not necessarily the case. We can think of trivial solutions that are robust, but have very poor performance. And we can think of most of what's done in machine learning right now is about increasing performance and not really worrying too much about robustness. So I think for me, that's the motivation, or that's the backdrop of what the word robustness means to me. And it carries from basically the theory of robust control to AI systems.
So robustness in critical systems, like in an airplane. Yeah. Even if it's AI, I think we need robustness, not only performance. So Jean-Michel, you want to add something?
Yes, as Liam said, robustness or robust algorithm aims to protect themselves from uncertainty and this can be seen at two different levels. You can think of a local robustness. This means that you want your algorithm to do not show a very different behavior when you have new observation, or you can try to measure how resilient to perturbation of global perturbation of the distribution of the input your algorithm is. So maybe we have to say a little about the fact that here I'm assuming that we are dealing with a machine learning algorithm where we train an algorithm based on some initial data, and basically what you learn is a distribution of those observations. And then when you want to use your algorithm, you measure the generalization property of the algorithm, and the robustness is about how well the algorithm can be generalized to local point, and this is what I call local robustness, or how resilient to perturbation of the distribution. That means you want maybe to use your algorithm for different conditions, not only the condition you have seen in the training sample, maybe closely related or maybe completely unknown, uncertain new events. And this is also about robustness. So I completely agree with this aspect of robustness is how the algorithm handle uncertainty.
So I will let Edouard say something about that, but you raise infinitely many questions in your introduction, both of you. So Edouard, you have something to add?
Yeah, so I agree with my colleagues. Those are different point of views, but the global idea is here. And what you mentioned in your question was also about certification. And for me, this is a part of the problem. So we could imagine that models are robust to some form of perturbations, but then for critical application, you need to prove that they are robust. You need to convince people, you need to convince authorities that they are robust. And this might be a harder question. I mean, it's very related, but building a model that is robust is something. Proving that it is robust is also a very relevant question, and especially in the context of certification.
Okay, so I think you raised, okay, I have to focus on one of the questions. I think you raised the problem that we have AI that is trained on some kind of data and has to be used possibly on different type of data, what is we call the out of distribution data. So basically a short story that learning theory is something that is not new. It exists since the beginning of machine learning. But the learning theory gives guarantee if the data on which you try to use your AI is of the same kind of distribution than the data on which you train the model, and then you have guarantee. And what you say, it's eventually this is not something that we can account of. We need to be able to train on some data and apply on out of distribution data, right? So what is out of distribution data for you?
Yeah, I mean, it's a very, very hard thing to define, right? I think even so the common, even the way that you phrased the question, and you know, I think Jean-Michel brought this up as well, is like there is this notion that there is an input distribution, that this thing exists. And I think for low dimensional applications, that's very easy to understand. That's very easy to conceptualize. But for high dimensional inputs like images, thinking that your input that there is some input distribution gets very problematic very fast. I mean, there has to be some kind of distribution, but to actually get a model that's able to some way understand what this input distribution is like trivial for humans, but extremely difficult for these machine learning based models. And so I think maybe the question is why? And I mean, I think at some level, the answer has to be abstraction, right? So our notions of in distribution and out of distribution are at some abstract level. Like I've never seen a giraffe before. I've only seen zebras. The giraffe is out of distribution. But machine learning models that are doing inference over observations that contain pixels, it's very tricky, because like if the sun has never been in that specific location when I saw a zebra, and now it's over there a little bit when I see the zebra, I mean, technically we're now out of distribution. So you quickly get to the degenerate problem of kind of very hard to actually model this like input data distribution. And so I think that, yeah, so the path forward has to be that we have to learn representations over these like abstract kind of concepts. And then we have some hope of actually being able to like define this out of distribution thing. But until we have that kind of a representation, it becomes very, very, it's very, very hard to even define. That's my personal opinion.
Mm-hmm. Something to add, Jean-Michel or Edouard?
Yes, I completely agree because, and it's a very old story in statistics where you really want to know where the information lies. And it's a question of embedding, and maybe so statisticians from decades have been trying to identify the particular areas where the true information you want to use is in the data. So you try to find embeddings, and maybe you want to try to find low dimensional manifold, and you want the data to be close to that. So you imagine something very low, and then you have the data which are just around. But the question is, you really need to find an embedding. What is completely new, maybe in machine learning or artificial intelligence, that this embedding also is not also on the data, but on what you want to do with the data. So this embedding depends on the algorithm you use. If you use a deep neural network, then it shapes an embedding, and you want also to use the algorithm as something that gives you a good decision, but that also digs into the data to provide a good embedding. So there is this duality. You have the world of the data, the world shaped by the algorithm that provides with this kind of representation. And this is something that people did not have before in statistics, where you try to process further your data to try to look or in statistics or in probability, and that is very interesting, I think.
So you have to understand it properly. To be able to see what is out of distribution, you need more than one example.
Yes.
Because you have a statistic point of view, and also, if I understand what Liam was saying, it's not any matters of pixels that can be a possible image, even if it's an out of distribution image. So we have to define what is possible, and among what is possible, what is out of distribution, right? Something to add, Edouard?
No, I don't have anything to add. Thank you.
Everything is fine for you?
Yeah.
So it's a very difficult question. I will try to point out these ideas, but in two different phases. Okay, so let's start to see what is happening with the problem of having in distribution data for the learning. But even with that, what are the problem that we have in the learning phase? I mean, I suppose that we can manage what will happen for the out of distribution, but already for the learning phases, there's some kind of problem that we have to look at. Let's say what you talk about epistemic and aleatoric uncertainty that are related to models or to the data. Liam?
Yeah, I mean, I think this gets really hard really fast. I think, like from what I was talking about in my talk earlier, we chose the regression problem and the aleatoric uncertainty problem because it's something we can wrap our heads around. That this notion of aleatoric uncertainty, that's the underlying uncertainty of the actual process that we're trying to model. That's something that we're comfortable with somehow, that there is a stochastic process and we have probabilistic tools to deal with stochastic processes. We've known how to deal with these for a while. But the epistemic uncertainty part is so hard. Like, to actually even think about what it means to calibrate your estimate of epistemic uncertainty is already really problematic. Like, what would you, I think before we even go down this road, we need to establish what are the desiderata, like what is it that we would actually want our model to output. And here I think I want to emphasize something that Jean-Michel also brought up. I think, in more and more cases, it becomes true that these definitions and these concepts become coupled with the task of what you're actually going to do with the information downstream. So somehow, you know, if I can build a controller, like, so say it's a self-driving car, this is where my mind always goes, because that's what I do. So, you know, if I have some controller that, you know, I have an object detector that's got 5 classes of things, pedestrians, cars, whatever, but I have the ability to also determine that there is an object, but I don't know what it is. Well, that's a useful thing that I can use in the entirety of my system. If there's some object that's there and my system has not been able to identify what it is, well, then I should probably stop or something, right? Like I can take action over that information. And so in that context now, all we need is a binary measure of whether we're confident enough or not confident enough. The issue of calibration becomes less crucial. But maybe in some other context, it's very important to have a more, you know, fine-grained and calibrated measure of how in distribution we are, how far away are we from the manifold, questions like this. But yeah, I don't know if that answers the question, but these are just sort of like musings, I guess.
I think you point out to something that is, there's a lot of question about that. Basically, you point out the problems. What is the difference between uncertainty and anomaly detection, sort of? And there's a lot of question about that in the chat. So maybe, Edouard, you have something to say about that?
Yeah, so I understood the question about being able to describe what happens during the learning phase in different conditions, in different contexts. And to me, this is about some of the big open questions in machine learning nowadays, being able to say, what are those learning algorithm doings, and being able to provide a priori guarantees that they are working well. So they are optimizing if they need to optimize, that they are generalizing if they need to generalize, or even that they are robust if they need to be robust. And for me, it's one thing to build a model that works for given some measure of criterion, but it's another thing to prove that it works. So building a model that works is something that people are able to do. But being able to explain why they work, or maybe to give arguments ensuring that they will work in a certain regime, in a certain restricted regime, is a much harder question. And I think we are really at the beginning, and mostly in the context of neural network and those deep learning methods. This is completely exploding. But being able to get a hand on what they do is really hard, and really, I mean, there are many open questions around this. And the parallel that I do, and it's not from me, I heard it from colleagues in conferences, but we had trains running on steam engines decades before the thermodynamics was discovered. That means that engineers are able to build things that actually work, and that they don't really need a proper theory for it. It's trial and error, it's empirical discovery. And I think that one of the role of researchers in machine learning and academics is to find a theoretical hand on the practice, and in particular during the learning phase.
Okay, so just let me see through to make some kind of my resume of what you say. It's so we need to have an AI that will be able to be robust if we are in some kind of slightly different setting, meaning that maybe in a situation where we have something that we have seen in the training set that has not been labeled, if I take the example of Liam, and being able also to be able to detect anomaly, or to detect when you really are out of distribution. Is there something that you have in mind? Maybe Jean-Michel? I try to just point what I think I understand of what we are saying.
So can I think, oh, sorry, go ahead.
No, sorry. The issue which were raised up to now are very complex, because we see that we mix mathematical guarantees to make certification. Then Edouard was trying to understand why an algorithm was not working. So it makes also explainability issues. Maybe you want to understand why some change of condition may prevent an algorithm to work. So in this case, it deals also with confounding variable change of condition and something which is well known, called causality issues in machine learning. So it's complicated, because certification deals with all this field all together to really understand basically what is learned and why an algorithm take one decision. And as Edouard said, we are very trying to run after the work of the engineers in order to provide the certification, but we are really trying to gathering energy in all these fields in order to provide. But people have to understand that it's not a very easy question that can be solved in a snap. It's something of kind of a progressing work with different point of view. So it's not the solution that does not exist, but different solution, different points of view. And there are several issues of Edouard was trying to provide proof of certification. We were trying to look at the importance of causal representation, a good representation, to look at where the information is. You can look also at causality. So it's I think it's all this together that can provide a framework to certify artificial intelligence, and not one thing in the field.
So a theory that will be able to deal with in distribution, out distribution, is something that we need to provide. And you say something about causality, Jean-Michel. I think, yes, we have to investigate this. Of course, machine learning is basically something that is related to correlation. And how can we deal with causality ideas? Yeah, it's a big problem. What you have some insight and maybe some also explanation of what a causality might mean from your point of view, because there is no one and only one definition of what it means. Liam, you seems to be eager to say something.
Well, so I mean, I was thinking about the train metaphor from Edouard, and I'm not really sure that the train metaphor is actually making the case for explainability. I mean, if we have trains, but we don't understand the theory of thermodynamics, but the trains work, then who cares? Like, why do we need to know the theory of thermodynamics? And so like projecting this onto our models, like, is input output certifiability enough? Or do we actually truly, like, what is the case to make that we actually need to be able to like to pull apart the curtain and see what the machinery is inside, just to play the devil's advocate, I guess.
So I don't really know what the answer is. So the reasonable answer is that it might help, but I'm not sure indeed that's the correct answer.
But again, what is causality for you?
Because if you look at causality, you could try to understand what change of condition would change the decision. So you want to try to go beyond correlation and to try to add some causality, in the sense that you want to really understand the propagation of an effect regardless of the correlation. So if you want to try to understand a construction of a counterfactual world where you could forecast what will be the effect of a change of condition. I'm driving in a sunny condition in the south of France. I have to make an emergency brake. I try to understand what will be the effect of the self-driving car if I was driving under snow, I think, because you are in Quebec. So
I think it's over for now, but yes, we have a lot of snow.
And to do that, to really try to look at the true propagation of the modification of one variable and look at all the chain effects. So, and this corresponds to different mathematical notions. You could try to think about a counterfactual model, or you can try to look at the way you change distribution and how you modify distribution, and this open the field of new research in optimal transport theory, for instance.
Yeah, but it's not so simple to implement what you propose here.
Yeah, but
how do you get rid of the correlation approach?
That's right. You can't infer it directly from data somehow. I mean, you're trying to infer something from observations. That's like, I don't see how, like, it seems very, very challenging to disentangle the correlation from the causation. But I mean, I completely agree from the standpoint, particularly of embodied systems. And it goes back to this question of abstractions and representation. I mean, if we have fundamental, if we're able to learn the underlying mechanisms, the true mechanisms that are governing the world, then that seems like the key to unlocking generalization in some sense. And that's how I think people are able to do it. Like we generalize, you know, when we get in a car when we're 16, it's not like we have no idea how to drive a car. Like, we're training autonomous cars based on just autonomous driving data. But when we get in a car at 16, we have all of this other understanding of the mechanisms of the world. And so we're able to like learn how to drive super fast. And to me, I think that's the key, like, so most kind of important thing that we can try and unlock.
We have 5 minutes left, so maybe we should try to wrap up. But if I look at the chat, there's a lot of people who are saying that there is no other solution than reinforcement learning to deal with all the problems that we have discussed today. I'm not so sure about that, but I would like to hear about what you have in mind about that.
I can start, but I'll try and be brief maybe. I mean, I think I view reinforcement learning as like I guess to take from Yann LeCun is the like cherry on the cake. It's the thing that you do at the very end to actually refine your policy based on all of the underlying understanding that you have of the world. And so I think, yes, this is like a tool that should be brought to bear. But I think that the larger question of representation learning, particularly self-supervised and unsupervised representation learning as a prerequisite for reinforcement learning is still the way to go. And there's a lot of work in this area right now to try and find clever ways of being able to either interact with the world or manipulate data or whatever to somehow endow agents with the ability to learn representations of how things work and what things are and things like that.
Learning representation, that's an interesting point.
Do you mean that in fact you could imagine a world where you could have artificial intelligence that can generate data that are very specific and with good representation of the information that then could be used to train the artificial intelligence that will be used to make the prediction?
Yeah, I mean, I think connecting to your causal like story, right? If we have the right representations of the world, then you know I can drop this pen and I might not be able to tell you like exactly where it's going to like end up on the desk, but I can take a good guess, and if I see where it ends up and I didn't see it fall, I can kind of tell you that makes sense. It seems like that was a reasonable thing that happened. And yeah, so I think that ability to predict into the future based on these representations is like the key for planning and being able to plan efficiently until we have these kind of, you know,
yeah,
ability.
but Liam, we have some kind of knowledge of law of physics. So when we want to have a built-in AI that will go into an airplane.
Yeah, so put those equations in there. I'm all for that. I think whatever priors, whatever inductive biases that we can put in that that help make that learning problem easier, let's go for it. But I think that's just like a question of learning tricks. I mean, I think I don't have to tell my 2-year-old that the gravity is 9.81 meters per second squared for her to be able to infer things about falling objects, right? Like it's not a requirement, but it could be. I certainly think that we can find ways of including that in our those priors to make things more efficient.
Okay. Jean-Michel, something to add?
No, I agree with this issue of finding a good representation of
a good representation, and a representation that will be broad, basically. But that's my understanding of what is causality. If you know how to deal with many different related situations, and your AI is working well, it's probably because the AI find the causal rule.
Yeah, it's trying to match the goals of the human. Human wants always to find the truth, and then we need to help the artificial intelligence to really find what is true and what is good. So, and what is good is what is causal. So all the ways you can do to improve the truth of the decision of the artificial intelligence to help her help it, I don't know, find the truth in the world of data is good.
Good. Edouard, something to add? Le mot de la fin peut-être?
Peut-être, rapidement. Yes, so there was discussion about interacting agents and reinforcement learning. So I'm not an expert in this field, but to me, in terms of the challenge in terms of predicting what it does and being able to prove and certify things is a step further compared to just describing one model. So we have several models interacting, and according to me, this really raises the challenge much higher.
So to have a lot of models and a lot of different contexts that are related, and a way to learn how to have a model out of that. This might be
and to put some guarantees, to get some guarantees on the behavior.
And find a way to get some guarantee out of that.
Yeah.
And this could become also from statistics, traditional statistics, but not only about that, I think, if I understand what you are saying.
Probably, yeah. I'm not sure I have the answer.
So looking at what is happening in the engineering world and try to understand it properly and to make some theory out of that, should be also a direction for the DEAL project, right?
Yeah.
So I think that's all the time that we have, and I thank you. And for everybody, let's meet tomorrow morning for people who are from Canada, and tomorrow afternoon from people who are from Europe. Otherwise, c'est le temps d'aller dîner. It's time to go to dinner, whatever the place you live, it's the same word. Okay.
Merci,
Thank you very much.
Thank you, François.
Bye-bye. See you.
Bye.